Okay, in this video I'd like to move on from the discussion of LEDs to the discussion of lasers. And the book has a lot of detail. You can read a lot about the laser physics and operation in the book, but I'm just going to give a very quick overview of it. There's three things you need for laser operation. You need to pump some photons into the region of space with some sort of a light source. That region of space needs to be a gain medium. And number three, you need to have that gain medium inside of an optical resonant cavity. In other words, you've got two mirrors facing each other. Okay? And the way the laser operates is, first of all, you pump some photons in there, here indicated as HF, and with a squiggly arrow coming from it. That photon is going to bounce back and forth between these mirrors. Okay? And if you have a gain medium, by definition what that does is it causes photons to induce stimulated emission. So a gain medium implies that we're going to have stimulated emission of photons. And these will be in phase and coherent with the original photon. Okay, so that's what a gain medium does, is it causes one photon to induce more photons bouncing back and forth. Okay, and then at some point you get so many photons bouncing back and forth that one of these mirrors is only a partial reflector, and the light finally emerges out of that mirror. This gain medium is characterized by a gain curve, and the optical resonant cavity is characterized by longitudinal modes. And what happens is, just as when we took a zigzag ray and drew a picture of the zigzag ray having a phase matching condition which gave rise to the modes inside of a waveguide, we will have the same sort of phase matching condition here, where we say that that the L is equal to the cavity length, and we say that 2L, which is the round trip distance, has to equal m lambda. Okay, where lambda is inside the medium, let's say lambda by n if we use the free space wavelength. This is the condition for phase matching. And what happens is, if you, and where m is an integer. In other words, it's again kind of like the waves on a string, the modes in a guitar string. And this gives rise to the following condition, that the frequency that resonates is equal to m times c all over 2nl. And so these are the resonant frequencies. And we can also write that the spacing of the resonant frequencies is delta F, which is C over 2ln. Okay, you can do the little math to straighten all these equations out for yourself, but they work. And this is then giving us a set of allowed frequencies for this gain medium. And so as a function of frequency, we have only certain frequencies allowed. Okay, with this spacing delta F. Okay, it turns out that what we do in laser diodes is we make L very small, and therefore the frequency spacing is going to be quite large, and we're only going to get a few, not too awful many, modes underneath what's called the gain curve of that medium. So the gain medium has some curve associated with it, which says, okay, in this frequency range the gain medium works. Outside that frequency range it doesn't. And so if we have a gain medium with this curve in red here, and I'll label that, that is the gain, I don't know what you can, gain profile of the gain medium. Then the profile of the laser is going to be these spikes as shown in red here. So there will be a few laser modes that are available underneath that gain medium. So and you can see a picture of this in figure 318 of the text. Maybe this is a better picture than the one I drew, but showing a laser diode with 819, 820, 821 nanometers, and the gain curve of the medium, and then the modes of the output of the laser. Okay, so this is the idea of how a laser diode works. And in fact, well, what I'll do is I'll come in on the next slide and show you a little bit about the material system and how do we actually make this cavity out of a semiconductor. Okay, thanks.